torque, if you apply 1 pound of force on the driver, it's the small gear right there, you can multiply that 1 pound by 4, and I guess in this example I wrote 5. So the output force is 20 pounds. All right. So that was how to calculate, I guess, the gear ratio. But there's another important thing you need to know is how to calculate like torque, or I guess it can also be called a moment sometimes. They mean different things, but for the most part, they're kind of interchangeable. Basically, very simple. It's just distance times force, right? So this is just like a drawing diagram, but you can think of this as a wrench on a bolt, right? So if your wrench is 1 foot long and you're applying, or let's say in this case it's 5.5 inches, right? And you're applying 15 pounds, you just multiply the distance by the force. And that's the net torque on basically the bolt which you're pivoting around. So that's 8.25 inch-pounds in this case. So that's technically what you'd call leverage. So you've probably heard that term before, but maybe not thought about it in its literal sense. All right. Okay, so one more time, because I'm going to keep repeating this because it's very important. MA is a ratio of output over input, okay? And then it doesn't matter whether it's, we'll see later, there's a bunch of different, I guess, values you can use, but you can be diameter, RPM, torque, teeth, all of those. It gives you the ratio, and that's the ratio that will matter. That's the ratio that you're multiplying to get whatever output. Another one note is that this ratio is theoretical, right? Whenever you have some kind of motion, say gears, belts, pivots, really any motion, there's going to be energy losses. And this is technically ideal mechanical advantage, so it doesn't account for the losses. But you use this to really estimate, and then you use something called a safety factor. So you basically add extra so that it's able to do the task. So it's a multiplier. So you multiply by this ratio to get your output, and it can be greater or less than 1. And now the most important thing after the fact that it's a ratio is that it's a trade-off. So you don't create torque. So we've been saying how before, where you could have a gear, apply 5 pound-feet of torque to it, and then on the output you have 20 pound-feet of torque. You didn't just create the torque. What happens is if you have higher torque as a result to a reduction by gears, or just a reduction in ratio, you'll have a lower output speed. And then same goes for the other way, where if you gear it up, which I'll explain later, you'll have lower torque. So I kind of explained that in the bottom left with some physics equations, where basically when you apply torque, you're applying basically work to it. And then I guess that becomes power. So you can't just create power. There's always going to be a trade-off versus work and time. It needs to stay in balance. So you remember that MA is a ratio. It can be thought of a multiplier. It can be greater or less than 1, and it is a trade-off. You don't just create energy. All right, Tommy?
Okay, so here you see some examples. Like this would be like the kind of thing in a car where like the ratio is being reduced down. So instead of getting the extra speed, you're getting more torque and more power. So then, and then here this would be a bicycle, and then in this example you're gearing it up. So as you can see, there's a good gear here that you're pedaling. That would be the effort. Yeah, and then it's the smaller gear here. So then there would be more speed and less power.
Yeah, so basically on the left there, that's an automatic transmission. So I don't know if people are driving, but basically your engine will spin pretty fast. Like it can go up to like can go from like 2,000 to like 8,000 RPM depending on what car you have. But probably realize that your wheels aren't moving at 8,000 RPM. It's because they're reduced by this. It's a transmission, basically. That's a fancy word for a gearbox, or gearbox really just means a compound gear train, or many gears used in series, basically. So it makes it so that your RPM of 8,000 RPM is much more manageable, and then you also get the torque to move a 2-ton car or whatever, a van. Whereas on this bike here, the wheel spins much faster than the pedals, at the rate at which the pedals are moving, because if you think of it as output over input, the sprocket on the left is really small, you'll see, and then your applied force, the one on the right, is a very large diameter. So if you were to take a small number over a large number, you're going to get a ratio of less than 1. If you multiply that to a torque, I guess it would be lower torque, but then that means higher speed. And in this case, the bike is pretty light, you're pretty light, so you can afford to get that extra speed. And that's why when you shift up in gears, it gets harder to pedal, but you can maintain a higher speed. Okay, so that was just the basics in explaining how mechanical advantage works. Now this is, I'm going to explain simple machines, right? So this is just basically a designation for mechanisms that change the magnitude or direction of force. So basically that's the lever, the pulley, the wheel and axle, and then also the incline plane, but I don't think we're going to have time to go over that today. Okay. Tommy? Okay, so the lever, you probably know more or less what this is. It's a simple machine consisting of a beam or a rigid rod, or some kind of, yeah, I guess a rigid rod, and it's pivoted at a fixed hinge, or more specifically a fulcrum, right? So the mechanical advantage, or I guess you could call it reduction in ratio, are the distance from the fulcrum. So that's the applied and the resistance forces would be measured from the fulcrum. So there's 3 types. You've probably heard these before, but you've also probably not remembered what they mean. There's the first class lever, the second class, and the third class lever. So that's the 3 at the bottom here. And you'll notice the differences are between where the little triangle or the fulcrum is placed, and also where the forces are applied. So the first class lever is generally a pretty ideal lever. This is where the fulcrum is located between the effort and resistance forces. So you could think of this as like a seesaw, basically. That would be, I guess you could call like a symmetric lever, where I guess most of the time, or yeah, a lot of times you'll see where the fulcrum is more or less in the center. So if you have people of the exact same weight, it would more or less balance. Now, if it's offset, you start to get a change in mechanical advantage, because if you were to measure the distance from the effort force to the fulcrum and the resistance force to the fulcrum, if you notice how the triangle there in the middle is closer to the effort than it is to the resistance. All right, so basically you have a large value for the resistance, and that's, I guess, the output, or that's how to explain this. Okay, well this here, you see it's a mechanical advantage of less than 1, because you have a shorter lever on, basically. So if you go back to torque, how to calculate torque, yeah, that's it. The distance from the fulcrum is the torque you're applying. So the resistance force has, if they're the same amount of force applied, the resistance force is, say, 5 pounds. I can annotate this. 5 pounds, right? And your effort force here is 5 pounds. Your distance here may be 2 feet versus 1 foot. So if you multiply these values to figure out the torque, you're going to have 10 pounds of force versus 5 pounds of force. So if you're applying from here, you're going to get a mechanical advantage of 1 to 2, so half. Your force is going to be halved, but this is going to move across whatever distance twice as fast. Again, that trade-off. And it depends on where the fulcrum is for the first class lever. So the second class lever, also I'm calling them by their names, first class, second class. It really doesn't matter if you know the names or not. I guess as long as you know the concepts, that's what matters. Anyways, the second class lever, the key characteristics of this is the fulcrum, triangle there, is located on one end of the lever. So if the fulcrum is in the center, it's always going to be a first class lever. But when it's on the side, the situation changes to where, or in this case, basically the resistance is in the center and the effort is on the opposite side of the fulcrum. So this will always have a mechanical advantage of greater than 1. Now, why is that? I can show you. So if you imagine again that this is 5 pounds of force going down and 5 pounds of force going up, and you have 1 foot from the pivot or the fulcrum for the resistance, and 2 feet from the effort. You multiply them out again, and you're going to have 10 pound-feet of torque. I'm not going to put units. And then you're going to have 5 pound-feet of torque. And since these are going in opposite directions, you're going to have, basically your ratio is going to end up being 1 to 2, or 2 to 1, also known as 2. 2 to 1, since it's output over input. I guess that doesn't really apply here. Yeah, anyways. Yeah, 2 to 1 ratio here, because your applied force is going to be double your resistance force. You're always going to, your effort force is always going to be with a longer lever arm. You're going to have more leverage than the resistance force. That's why it's greater than 1. All right. So for the third class lever, basically the fulcrum is still located on the end, but the location of the resistance and effort forces are reversed. So they're still opposing, but the effort force is in the center this time, and the resistance is on the outside. So similar to the other one, this will always have a mechanical advantage less than 1. So the second class lever has it always greater. This has always less than 1. For the same reason, just since the situation is different, you have more leverage. The resistance has more leverage than the effort force. So it's going to have more torque. But again, this applied force, the effort force here, is going to move the resistance force twice as much as this moves. So if this moves 2 inches upward, or I guess around the curve, 2 inches, this would move 4 inches upwards. But you'd have half the amount of, I guess, force. All right. I don't know. That was a bit chaotic the way I explained it. Do you have any questions? I've gone over, I guess, levers and mechanical advantage.
Nick, I would point out that the third class lever is probably the most commonly seen in our robots because it's the way the air cylinders would push on the ball intake to deploy it.
Yeah.
When we use air cylinders, it's typically third class.
So actually, a lot of the times, you'll see the third class lever used. I guess you see around school sometimes there's like forklifts and stuff. I don't know about forklifts, but like the large cranes, they usually have a hydraulic piston in the center. And what that ends up looking like is basically you have this large crane here, right? And you have your hook on the end, and it's attached to some driving platform, and then whatever these tracks here. And then you'll have a hydraulic here, right? So whatever your force is pushing down, right here. This is your resistance force. And then you have your applied force here, which is the hydraulic, like that. So it's common because first here, it's easier to package. It's really the only way you can package it. And because of the way hydraulics work, you can get a lot of force out of them still. So they're carefully placed such that it can still support the amount of weight being held up. So if you notice, I drew this more or less in the center. I think that's where they're placed, kind of. But if you were to place it so that it was right back here, and you're trying to apply force like that, your leverage becomes considerably smaller, because the distance from here to here, that ratio is just going to be so large, you might not even be able to carry whatever load you're rated for. But similar to the way we carry or we lift intakes on a robot, it's in the same way. This is a drive base like that. And you have some sort of support here, and you attach your pneumatic piston. Force of gravity, your applied force. All right, the resistance force and your applied force upward from your piston. Right here, resistance, effort, third class lever. So again, we also are careful in placing the location of this pivot, because if it's too close, this piston won't be able to lift it. And if it's too far, it's probably not going to be able to package properly. But I guess that's for later. All right. Any more questions? I want to make sure mechanical advantage, the concept of that is clear. Otherwise, none of this is going to make any sense. All right, let's go. Okay, so next is the wheel and axle. So this is basically a wheel. In the end, is just a lever arm fixed to a shaft called an axle, right? You see this diagram here. This is probably not a way you've thought of a wheel before, right? A wheel is just, I guess, something abstract, but here it's basically just a bunch of second class levers, or I guess it depends whether it's a second or first class for how you're driving it, but it's just a bunch of levers in series. And then somebody decided to put something around the outside. And because of that, you get the effects of the first or the third and second class lever. So I guess it depends if you're driving the wheel or it's driven by the center. So you could think of it in a car as the steering wheel versus the driving wheels, like the tires, right? So it's important to know if the axle is driving it, like the tires, or the wheel is driving it, like the steering wheel is driving the steering system, right? Because that changes where the applied and resistance forces are. Is my only slide? You got more. Okay. So what's the IMA of the wheel, or just mechanical advantage? If you're driving from the shaft in the center, right, you're gonna have a 6-inch diameter, right? So you have 6 inches out from the center point, or the pivot, the fulcrum. And then your resistance force, the outer diameter of the wheel, is 20 inches. You're gonna get a, I guess, overdrive, or loss in torque of, I guess, 0.33, or 1/3, versus, so that's if you're driving it by the axle. But if you're driving it, it's like a steering wheel, moving the wheel so that the shaft moves, you're going to get the inverse of that, basically. So it's 20/6. Again, you got to remember, it's output over input. So the output is going to be the 20, and then the input is the 6. So you end up getting a ratio larger than 1. So your torque is multiplied. All right. I'll show later how that basically works with gears and I guess both pulleys and sprockets. Okay, so this is, I guess, one type of pulley. I'm going to show something later that's also a pulley, but I guess the more specific designation for that later is like a timing pulley. But this pulley, at least in the simple machines context, is basically a wheel with a groove in its rim that's used to change the direction and or magnitude of a force exerted by a rope or cable. So I'm sure you guys know what pulleys are. They can these are also, surprise, surprise, they can act as levers because in the end they are just also a wheel. So there's two situations on the right. So if you notice the locations of the pivots or the fulcrums here, this one is the fixed pulley right here. So it's just stuck here and there's a rope going over. So this is a first class lever. So this is gonna have, and it's a, I guess, symmetric first class lever. So the distance from the fulcrum is equal on both sides. So this would have an IMA of 1. Since output over input, it's going to be the same number anyways. So it's 1. And all this does is changes the direction of the force, right? Think of it this way. You're applying a downward force, but the net force is ending up to go upwards. So you can lift something by pulling down. That's what a fixed pulley can do. But there's a second way you can use pulleys that I don't know, might not be as intuitive, but a movable pulley, right? So that's what this situation is here. So this is a second class lever. And here, the force direction stays constant. You're pushing, or you're applying an upward force, and the net force is going upwards. And the key with this is you get a, I guess, a mechanical advantage of 2. Because again, this is symmetric, right? Since you have a diameter and the fulcrum is in the center, or I guess in this case on one side. So if this is a 2-inch diameter pulley and you have 1 inch, and then also you have 1 inches or 1 inch out for your applied or your resistance force and 2 inches out for your applied force, you're going to have a ratio of 2. And this movable pulley is going to give you a mechanical advantage of 2. So those are, I guess, the main ways we'll see pulleys used. All right. So now before we move on, I want to ask, do you have any more questions about, I guess, pulleys, wheels, levers, or mechanical advantage? Okay. So this is the, I guess this is what everything before this has kind of been leading up to, or also the next thing, but compound machines. It's not too often that you see these systems used on their own because just one gear reduction or one lever isn't very, like to get a lot of reduction, which is what you typically need, it starts to get very kind of cumbersome or I guess ridiculous if you were to think of some ridiculous situations like, okay, never mind. Anyways, the compound machines is how you solve that. How do you get a large mechanical advantage without having a ridiculously large system, like 2 large wheels? And that's with the compound machines, or with compound machines, which is just a bunch of separate, simple machines that the output of one system becomes the input of another. So basically, if you look here, this is a bunch of movable pulleys, and they're hooked up in, I guess, what you could call series. So basically, when you start out here, you're applying 10 pounds of force. And through this first movable pulley, you have a mechanical advantage of 2. But this pulley is pulling another pulley, a movable pulley, with a force of 20 pound-feet because of this mechanical advantage of 2. but because it's a movable pulley, you have another mechanical advantage of 2. So now you're gonna that is lifting another movable pulley with 40 pound-feet of torque, since it's multiplied by 2 once again. All right, and that's finally moving an applied force of 80 pounds. And this is a mechanical advantage of 2. And you see here on the left, what's the ideal mechanical advantage of this compound machine? It's 8, because there's 3 pulleys, or I guess there's 4. Actually, how's that? 1, 2, 3. Oh yeah, 4. Basically, there's 3 pulleys, and the way you get the net mechanical advantage is by multiplying the mechanical advantage of your simple machines or your separate systems. I guess you get your compound system. So that's why your 10 pound-feet of torque, or your 10 pound-feet, is able to lift 80 pounds, because mechanical advantage of 8, you just have 10 times 8, and you get 80. All right, so that's how compound machines work, and that's how you get the net mechanical advantage or gear ratio of systems on a robot. Because a lot of the times you'll have things like gear reductions, and then chain reductions, and then there's a lever arm that you have to figure out, or maybe there's a wheel and axle. So I'll show examples for that later. All right, so we're finally to power transmission. So we've gone over mechanical advantage, and we've gone over simple machines. Now this is the power transmission methods. I guess the ones you'll typically see in FRC, and really most anywhere else. I'm sure there's more that I'm missing, but these are the big ones, and these are the ones that you should know about for the purposes of designing a robot. So the 3 are gears, pulleys, and sprockets. So from left to right. All right, that's good, that's good. So this is what I was probably alluding to earlier, where there's a bunch of values you can use to get the ratios of your mechanical advantage, or your gear ratio. You can count the number of teeth, you can count the diameters, you can use their angular velocity, or also known as speed, called RPM, or their torque. I think there's probably something I'm missing here, but those 4 are the easy ones. And if you know those values, then you can figure out the gear ratio. So in this case, why is that reversed? I feel like this should be the other way. Anyways, this is a ratio of 2 to 1. So you get a gear ratio of 2, mechanical advantage of 2. Here, can somebody tell me why? In the chat. Anybody have a guess? They know. The key here is you can use any of the values: number of teeth, diameter, RPM, or torque. Yeah, basically. So your applied, or the diameter of your applied, I guess your effort side, your powered side, the red gear, the input, is going to be, it's half the diameter of the blue gear, the output, right? So remember, it's output over input. So 4 over 2, 4 divided by 2, 2, right? Or you could simplify it, 2 divided by 1. That's where the 2 to 1 comes from. And that's your gear ratio there of 2. All right. Next one. Okay, so this is some, I guess, characteristics of gears. A lot of the times in FRC and just in general, you'll see a lot of belts and pulleys, as well as chain and sprocket, right? And if you don't know what that is, I'll explain it in just a second. But those will rotate in the same direction. So a lot of the times, you want things to rotate in an opposite direction. So one of the ways you can do that is with gears, because they will rotate in opposite directions. So if you look at the blue gear and the red gear, if you imagine turning the red gear to the left, right? If you imagine turning it to the left, these are essentially stuck together, right? With its teeth, they'll push each other. So that means this will rotate clockwise. This is rotating counterclockwise, this will rotate clockwise. So an even number of gears, or just 2 gears, will rotate in opposite directions. Now, an idler gear, right here, or this red here, will allow 2 gears to move in the same direction. So what this is saying is basically, or I guess the general rule is, if you have an even number of gears, the input and output will be moving in opposite directions. But if it's an odd number of gears, they'll move in the same direction. And you can imagine here, if this is moving clockwise, this will move counterclockwise, which means this will move clockwise. And would you look at that? These two are moving clockwise. So it's kind of like, you could think of it as like odd and even, right? If you have two gears here, or just any even number of gears, they'll move opposite. And an odd number, they'll move the same direction. Now, using idler gears is, as you don't see it too often in FRC, because of the reason you'll see in the next slide. Okay, because idler gears do not contribute to the overall ratio. So they'd only really be used to either create distance between your input and output gear, or change direction. So they don't change the gear ratio, but intuitively that might not make sense, but it's the math works out. So right here on the right, over here on the right, it's showing the ratios between each of the gears specifically. Basically, they're isolating the systems. So from A to B, if A is the driving gear and 12 is the driven gear, output over input, you get this one ratio. So it's 0.6 to 1. And then here, 5 to 12 from this here, and you get 0.42 to 1. And then finally 20 to 5. And then when you multiply them all together to get your final compound gear ratio, it ends up as 1. Because essentially, it's just these two outer gears that are interacting. And that's your output over input, 20 over 20, 1 over 1. Your gear ratio is 1. So you might be thinking, okay, but if you like go up a little bit, you saw like a bunch of gears, right, all like packed together. Why are they there? Are they just there for fun? Like what? No, they're not there for fun, because that's actually a compound gear train, right? So a compound gear train is the same thing as, I guess, a compound machine. Basically, it's chain gears. One input of the gear, or one output of a gear is the input of another gear train. And this works because basically the yellow and blue gears are fixed to the same shaft. So that might not make sense how basically there was a gear in the center for the idler gear, right? Same as here, it is here. So why does this act differently? Because basically you could think of the wheel and axle at this point, right? So if you have a ratio of 2.5 here between the red and the blue gear, and then a ratio of 4 between the yellow and green, you can multiply them together, because this is basically one, I guess, one body, okay? You can think of it as like a shaft in the center driving a wheel. If you go back, here, Tommy, could you go back one?
Yeah.
Let's see. So the speed of the gears on the outside are going to be the same, right? Because of that 1-to-1 ratio. If you were to put those two outer gears together. The speed from A to B is going to, I guess from here, since the 0.1 or because the 0.6, the speed is going to increase. And then there's another small ratio, a ratio less than 1. So the speed is going to increase once again. So 0.42. But once you get to the last gear here, C, you're going to have a ratio of 4. So it's going to reduce the speed. And I'm talking about speed right now. You could think about it as torque too. You get higher torque, or you get less torque, you get less torque again, and then because of the ratio of 4, you gain it all back. So because you're multiplying them all together, you basically, I guess, lose your effect of the last gear. But if you go back forward to the compound gear train, since the yellow and blue gear are moving at the same speed, since they're on the same shaft, you can think of them as the same body, right? They're essentially one thing. When the red gear applies a force to the blue gear, or I guess the green is the driving gear. So when the green gear applies a force to the yellow gear, it's going to be multiplied by 4. So let's say you got 2 pounds of force right here, and then it's going to multiply by 4. Now, right here, since this is moving with at the same speed and it has the same amount of torque applied to it, it's going to apply 8 pound-feet of torque to this blue gear, to this red gear, since this is moving at the same speed, and then that's going to be multiplied by 2.5. So this works because as opposed to the idler gear, it doesn't lose its ratio in between. This is a compound system. I don't know if that was very clear. Do you have any questions? All right, we can move on. Hopefully this makes a little more sense when I show some more examples later. All right, so this is an example of just very simple, just 2 gears. Right there is that's just one of the standard motors you'll see in FRC. One of these things right here. That's a pro motor. And this is a small gear right here, and this is the driving gear. And then it's the driven gear is this large gear right here, and this is a shooter wheel. So actually, right here, you probably notice that there's the gears, and that's you can think of that as one reduction system here, right? Maybe that's a ratio of, let's say, 3 to 1. Now, if you think about the final ratio, for the purposes of shooters, a lot of the time, you're looking at surface feet, which is basically as a wheel spins, how fast is the surface of this wheel moving? So I guess you calculate that with you find the circumference, and basically you do some stuff with RPM. But basically, if you could think of, if you have a loop of paper and you were to cut it, lay it flat, that's like one rotation, that's the circumference. And you use that to calculate things like surface foot. But since this is a wheel and axle, so you have a 1/2-inch shaft, and it's a 4-inch wheel, you're gonna have a gear ratio of, or a mechanical advantage of, less than 1. So that ratio of 3 is going to, in the end, be smaller. So the actual applied torque to the ball, well, actually you don't really apply torque to the ball, but the surface foot is going to be higher because you have less torque. Okay, so we've talked about gears already, but the thing with gears is they have to be touching each other. They have to be right next to each other. And one of the ways you can get them to be, I guess, distanced a little bit is using idler gears. But the thing with that is basically gears, typically they would need to be fixed to a shaft. And then because of that, they probably need bearings, and then it starts adding a lot of stuff onto the system. And if you're trying to get two gears far apart, there's easier ways to transmit power that way, such as the belt and pulley. So we talked about pulleys earlier, which were the, I guess, like bearing pulleys or just like idler pulleys. But this here is, I guess I said technically it'd be called like a timing gear. I guess these are used on car engines too, if you're gonna keep comparing things to cars. But if you see, there's grooves in that belt right there, and those grooves allow the grooves in the pulley to transmit torque via the belt. So unlike gears, the rotation is in the same direction. I don't know if that makes sense intuitively. Basically, if you were to turn the pulley to the right, this belt is going to want to move that way, and this belt is going to want to move that way, which is going to make this pulley move in that direction. So in the end, it's going to move in the same direction. And you could think of it as the belt as a way to basically, instead of having these fixed on the same shaft, you basically take them apart, move them like this, and then put something in between so that they're linked together. But the main characteristic is this is a way to transmit power over long distances, and they can be quieter, lighter, and more efficient than gears, so you don't get as many losses in power through friction and other stuff and noise. The way you calculate the ratio is the exact same as gears. Again, so you can count teeth, you can look at the diameter, torque, RPM, and find the ratio. So if the red is the driven, yeah, why don't we do this here? If the red is the driving gear right here, drive, and the blue is the driven gear, or driven pulley, what is the gear ratio? And remember, it's output over input. I guess. Three. All right, so I saw two people answer 1 to 3. So basically, that would be the case, but if it was reversed, right? So it's 6 over 2 basically. So you're gonna have 6 is the output, or I guess you could use whatever other numbers you want. You could use these weird torque numbers, but oh, I guess you guys were probably looking at the RPM. Oh shoot, 30 RPM to 10 RPM. Oh right, so that's because of basically the torque is multiplied here, but that means the speed is reduced. Okay, I guess that's something I kind of know intuitively, but if you're looking at I guess it's safer to look at the diameter or the teeth numbers when you're calculating mechanical advantage. So, I mean, I understand how that would happen, but yeah, 6 over 2, ratio of 3. That's why your torque is higher on the output, so from 18 1/3 to 55 pound-feet, but your RPM is split, divided by 3. All right, and then key thing here, that's a pulley, not a gear. Don't call it a gear. All right, Tommy, next one. Oh, actually, examples. Oh, robots, finally. Okay, so here are 2 ways, or 2 things I found for places pulleys are used, pulleys and belts. So that's on the left there, that's like an arm, it's spinning like a shaft in the middle. So that's okay, that's a or this is a motor here, the 775 Pro motor you saw earlier on the shooter. And then this is basically a compound gear train. It's planetary gears. I'm not going to explain those now since those are considerably more, I guess, hard to understand. But there's a one stage of reduction in here. So this is probably something like, I would say 30 or something. And then there's this belt reduction here. So the key thing here is they could attach this motor just like straight on here. But that packaging is like, it's not very good. The pivot, it looks like it's up here. You don't want too much swinging around the back, and it's not very safe for the motor to be able to, I guess, just get hit off the back. And it's a really easy solution where they just bolt the motor to the side of the arm and use a belt. And by using that belt, they can use a small pulley here and then a slightly larger pulley here, then actually get reduction. And the good part about this is even if it's a small ratio of like 1.5, this 1.5 ratio is multiplied by 30. So your 30 gear ratio through this first reduction here is multiplied by 1.5, and you end up getting a ratio of 45 for not too much extra work. It's a lot of benefits here for packaging and also ratios reduction. And then there's something on the right here. This is a swerve drive that I talked about. A swerve drive last week where basically there's 4 separate motors in the corners, and right here it has inverted motors. So you can kind of see the motors up here inverted, but basically they use a belt to be able to have the motors in a different location in relation to the shaft, but still be able to power them. And then they also took advantage of the fact that they're using a belt and pulley to squeeze out some more reduction. All right, and then here's the last system we're talking about today. It's the chain and sprocket. So this is pretty similar to a belt and pulley, to where the main thing with this is you can transmit power along across a long distance. And it's, again, calculated the same way as everything else. Rotation is the same ways, or same direction for input and output. It's basically the same thing as a pulley, belt and pulley system. But it can be just as efficient and even more robust than a belt. And then I'll explain a little more in the next slide. But basically, it has this profile here that's, I guess, the negative of this chain. And this chain and the grooves in the pulley, or the sprocket here, allow torque to be transmitted. And then this is a sprocket, not a gear. A lot of times this is called the gear, but you use a chain to transmit the power, not the teeth itself. All right, Tommy. And here's an example on a robot for where a chain is used, chain and sprocket. So you see these a lot on arms and intakes. So this is an arm here. And basically, let me get the drawing again. This is the input here. And then there's a view on the right of the actual gear train. And then there's the output right there. So again, you notice large sprocket, small sprocket, and then this is the effort force, and this is the resistance side. So many times, most of the times, you'll see large to small because that gets you reduction, and usually you're trying to find a way to get as much reduction and in as small a package and a light a package you can. So this is actually a compound gear train. It uses, I guess, all 3 things we talked about. So again, this is your motor here, and it starts off with a belt reduction here. So there's a little pulley that powers another pulley down there. You can't really see it, but that feeds into a compound gear train. And then this shaft in the back there, you might not be able to see it very well, is actually this right here. And this pulley here powers, or this sprocket here powers the output sprocket. And finally, since these are fixed together, this entire system will move out. All right, next slide. This was the last slide. Okay, so this is the comparison between, I guess, chain and sprocket versus belt and pulley, since this is something I hear a lot of times where it's like, why would you use a belt and pulley over chain and sprocket, or the other way? There's a time and place for both of them, but they're both generally interchangeable. A chain or a belt is strong, but a chain is stronger in some cases. The chains are typically cheaper, but that's not a fact. Belts can be on the expensive side, but that's also not a fact. But this is just in general. Now for the actual operation, belts are a little more prone to slipping. You'll see that, I guess, a little more often. They're quiet, they don't need lubrication, and they don't really need to be tensioned so long as you design them in correctly. Now chains, most of the time, they do need to be tensioned because they can stretch and they need lubrication, and typically you don't see belts ever like breaking, but chains, their catastrophic failure mode is they just like pop at some point and they break, because they're made up of a bunch of links. Chains are heavier and belts are on the lighter side. I guess that's it. All right, so that was it for today. I guess, well, pretty much right on time. All right, so to review that, basically we've gone over just now mechanical advantage, simple machines, and power transmission. So I guess I thought that was like the last prong of, I guess, getting started with designing something from scratch. Yeah, okay, there's the form. So the main thing to think about when you're designing stuff is, first of all, when you're powering things, you should think about how to place your motors and transmit motion. And then for torque, I guess long unsupported structures, if you push on the top of them, if you think about the lever arm or the moment on them, there's going to be a lot of forces acting on it. And that's probably not a good thing on a robot when you're banging it around. So just thinking about, hopefully after you've looked at these slides, maybe you can look back at them, you can start thinking about where those forces would be applied when you're designing things. And hopefully next week we can start trying to design some stuff in CAD. And of course, we'll be here to help you. So Tommy just sent a Google form in chat. So could you please fill that out? Basically, I think it's like a feedback form into some stuff in there. And that's just so that we can try to adjust the workshops and just get some feedback. All right. Thanks for coming, everyone. I think